Thanks. So thank you so much for this. I also wanted to say just thank you to the center for holding this event and for everything they do. So economists usually are out there pretending like we understand everything. You're a physicist, I know more about physics than you do, right? That's sort of our reputation, and it's well earned, let's put it that way. So I've asked Ed and Gail and so many dumb questions about buildings and how they function that have really improved my work, and I'll talk about that a little bit. So we're going to do questions at the end, but if there's a clarifying question in the middle, just start waving wildly, and I'm happy to answer questions throughout. But what I thought I would talk about a little bit today is a number that is crucially important that usually most people haven't heard about unless you have some really weird reading habits, or you develop really, really large plots of lands with new buildings. So there's been quite some developments coming out of science that are crucially going to inform policy, federal policy, over the next few months. I don't think prior to the midterms, but probably thereafter. And I just talk to you a little bit about what happened over the past few months. All right, so let's just get some facts out. I know this is a room where people self-select into. You're probably reading 7 newspapers. You know what climate change is. I don't need to talk about it. But there's a couple of things out there where we just need to create clarity with some data. So every time I'm in some room where people don't worry about energy consumption very much, they're like, greenhouse gas emissions went way down during COVID. You know, things are much better now, and it's all going to be okay-ish. So I would like to just visualize that that's just not true. So these are CO2 emissions from fossil fuel combustion. So land use stuff isn't in here, but you know, we basically shut down most of human mobility and large parts of the world economy, and we had a little blip right there. And we're right back to where we were going thereafter. So no, things are not okay. All right, that's the first fact. The second fact is it's my son's bar mitzvah this weekend. So I have some relatives coming to town and I have to do this. So these materials will be used at dinner just to say, no, you're wrong, I'm right. So my colleagues at Berkeley Earth, which is a fantastic project on campus, where Dick Mueller and Saul Perlmutter, who have won Nobel Prize between the two of them, basically said, we are going to reanalyze what the IPCC did. We're going to buy the universe of temperature measurements across the planet with some money that was given to them actually by the Koch brothers to just see whether this increase in temperatures is just an artifact of people who don't understand numbers. So they spent a lot of time crunching these numbers. It's a really cool project now with larger staff that's looking at air pollution too. But if you need good graphics for your presentations, go there. This is the average for California. And what we're seeing here, and for those of you who like graphics, I was really proud of this. I did this last night. It took me hours to put the stripes that we have ties and now pillowcases of warming stripes right underneath here. But what we're seeing here, basically, pretty much a level of average temperatures for California. This is average temperature. You can do it for you know, nighttime temperatures, max, min, whatever you want. But you're really seeing here that since the late 1970s, early 1980s, there's this upward trend in California averaged. You can go in and look at the Central Valley. You can look at San Francisco. You can look at Beijing, wherever you want. It'll spit out those numbers for you. This is not IPCC stuff. This is just objective reanalysis. And Dick wrote an op-ed in the New York Times. I think it was called The Conversion of a Skeptic or something like that, saying, I've looked at the numbers. I agree. So thank you. So yes, emissions continue to go up. Yes, it's getting warmer. And we, of course, all know that CO2 works with a little bit of a lag, right? The stuff we emit now results in warming later. So there's a bunch of warming already baked in, even if we stop emitting CO2 right now. Okay, so I hope this works. So this was another little coding thing. This is what happens when Max sits down at his computer with like 2 glasses of red wine and says, I wonder if I could pull off the following. So let's see if this is animated. So here you have global CO2 emissions from 1850. This is sort of when we started calculating what they were. And I'm going to start in the year 2000. The black curve is observed emissions up to that year, and then I'm going to move that year out. And the red curve tells us where emissions are going to have to go globally if we want to limit warming to 1.5 degrees. I don't know how optimistic you are. I am one of the most optimistic humans on the face of the planet. I do not think 1.5 degrees, or there's a 0 chance that we're going to get there unless there's some sort of miracle. All right. I like miracles, but they just happen very rarely, which is why they're called miracles. So the basic notion here is, if we want to meet 1.5 degrees, and we would have started getting on the right path in the year 2000, you would have had to be in the red curve. So clearly we didn't. So I'm just going to move this forward. Oh, it's working. I'm so excited. I made my son calls it, I think it's called a jiffy or something like that. But what you're seeing here is the reduction path, right? The mitigation path we need to get on almost goes vertical, right? So it's equivalent to saying stop now. This doesn't bode well with the stuff I started out with, where it shut down most of the world economy and you're seeing a little blip. Caveat here, for those of you who work on this stuff, there's a bunch of stuff wrong with these carbon budget figures, right? There's no direct air capture in there. If we figure out sequestration, uncertainty is not reflected in there, but it's just graphically, I think, a pretty good visualization of what that looks like. Okay, Max, you picked 1.5 degrees. We all know we're probably not going to get there. I'm going to get a whole bunch of hate tweets later for saying that, I'm sure. But what about 2 degrees? 2 degrees seems reasonable. I think 2 degrees is sort of the equivalent of losing 25 pounds by Christmas, but it's doable, right? There are 8 weeks to go. If you do 2.25 pounds per week, you can do it. All right. So I'm sorry, it's after lunch, so I know this is a grave topic, but a little bit of light humor after lunch is important, otherwise nobody pays attention. So let's do the same exercise here. Does this look like any more doable if we start now, right? And the thing still, by 2020, like, I would not want to ski that slope. And I've been skiing for weeks every winter since I was 2. I'm too old now, my knees hurt. But it requires really steep mitigation paths. So the question then becomes, if we want to get anywhere close, or if we want to limit warming to somewhere between 2 to 3 degrees, it's going to be an all hands on deck kind of situation, which nobody knows better than folks that work on buildings, right? So I wanted to talk a little bit about what this mitigation future means in the context of buildings, and give you a little bit of how economists think about getting us into that right direction, or setting incentives that move us towards a path where we're going to limit warming to a reasonable degree. The other thing I'm going to say is, yes, I'm trained as an economist, right? That's the way I think. I think of, somewhat rational individuals making choices in the face of scarcity, but political constraints are real. Right? So political economy is sort of the intersection between political science and economics. To me, it's right now the most interesting part in the whole social sciences landscape. It's how do you create regulations, taking both economic constraints as real, but also acknowledging the very real political constraints we face. So, we read this. I just use this slide sometimes. This was in February. This was the actual front page of the New York Times, and I didn't cut and paste. That was a screenshot. The top says IPCC report came out, things look really dire, and right underneath we were informed that the Supreme Court is really thinking about what to do about CO2, and that battle has not been settled yet. Things look a little bit better, right? We're seeing a lot of investment going into climate mitigation. If you saw that amazing graphic on the New York Times yesterday and today, where they said what the Biden administration had asked for in terms of investment and what they actually managed to push through, the climate piece of the pie was one of the largest pieces of the pie, and also the one that was least affected by sort of cuts. So there is a big push, and a lot of that push relates to electrification and infrastructure. Okay, So you ask any 100 economists what the solution to climate change is, 100 of them, and some of them will vote twice. So you'll probably get 105 votes saying we should price carbon, right? What this basically means is most of the economy, unless you live in California, Europe, and parts of China in certain sectors, we're using the atmosphere as a free dumping ground. So you're not paying for the use of the atmosphere by emitting CO2 from your buildings, from your car, from your agricultural activities. And what we should do, at least that's what, University of Chicago economists even tell us, and they're usually not known for their progressivity on environmental policy, is we should make firms internalize the damage they do. So they should pay the price for how much damage one unit of carbon does emitted, and then you can make an optimal decision. Sort of like you've got to pay for the full consequences of your production activities. It is, if you need another econ class, I've got one for you that you won't fall asleep in, that teaches you this with calculus and all kinds of things. It is beautiful theory, and it actually does work despite what you often read on Twitter. Twitter is a non-peer-reviewed source of information, in case you're wondering. Okay, so what you're seeing here in red is all the jurisdictions that have some carbon price in place. So of course, in California, we're oh so proud. We're up here. We have our California cap and trade system, a really complicated way of regulating CO2, but it does work. There's a price on carbon that's not zero. The biggest one in the world is still the European ETS, the emissions trading system, where you get a right to pollute. And if it's cheaper for you to reduce your emissions, then you could get for your permit, you're going to reduce the emissions and sell them to somebody else for whom it's very expensive. The beautiful thing about these markets is you can read off what it costs the marginal firm to reduce 1 ton of emissions. So in Europe, the price is now fluttering around 100 euros somewhere. So it's pretty high, much higher than what we have in California currently. So great, Max, carbon pricing, but it's a global problem. So we're going to have to do something about this globally. It doesn't help us if only a couple of these economies are doing something. So we need to do more. So just to give you a flavor, and by the way, I'm happy to share these slides. If you see anything you like, you can just lean back, eat your chips. You don't have to take pictures with your iPhone camera. I'm happy to send you these high resolution slides, and you can use them as you please. There's nothing confidential on here. But it's not just the fact that you have carbon pricing. It's also the fact of how high is the price, right? So if a ton of carbon does, let's say, $185 worth of damage, but you're only charging firms $1 for it, right? That's like selling Ferraris for $10,000. That's not right. You want to charge the full price. So we see a lot of variation, and I'm going to use this number $185 a lot because that's the latest science. But the prices hover, they're very much clustered between 0 and 50, and then there are a couple of jurisdictions who are north of 100, Scandinavia mostly. We are very excited about efforts we're seeing in China, where the electricity sector is slowly becoming subject to a carbon price, but we're going to see how that goes. So verdict's still out, but there's certainly a lot of efforts underway to make something happen there. Okay. This is what I want to talk to you about for the rest of my time today. So this is the nerdiest number in all of environmental economics, but I also think one of the most important and one of the most policy relevant numbers there is. This is the social cost of carbon, and I'm going to refer to it as the SCC over again, not the SEC, not the people auditing you, but the SCC social cost of carbon. The social cost of carbon is a number. It's a price that you don't ever explicitly pay, all right? So if you have a cap and trade system or a carbon tax and you emit carbon, you actually pay that, right? So you have to pay a bill for your permits, or they're given to you for free some places. So you actually physically pay those, and then they appear on your profit and loss statement. The social cost of carbon is not that. It's a number you don't explicitly pay. It's the damage 1 ton of CO2 does over its lifetime, which can be thousands of years, across all sectors of the economy agriculture, energy, migration, conflict, keep on going, across the entire globe. So now you're sitting there is like, whoa, Max, how do you do that, right? I'm having trouble figuring out the BART schedule on how to get home and what that's going to cost. How do you figure out a number like that, right? How do I value the damages hotter temperatures cause in the year 2200 in corn-growing regions of, the central United States? It's really hard, right? And I'm going to try and convince you now that A, we need this number, B, we have a much better estimate of this number, and C, the federal government is using this everywhere at this point. So you should know it, and I'm hoping that in a maybe not so boring version of a lecture, I can convince you that this is a really cool thing to do. Okay, first off, I'm going to pull out another Nobel Prize, all right? This sounds a little hippy-dippy, Max, right? So you've got like a number, a price that you're going to make up that's going to tell me globally how much damage CO2 is going to do. 1 ton of CO2 is roughly what you emit if you drive a Mustang, Ford Mustang 5.0, not the small one, the big one, 5.0 from San Francisco to Chicago. That's 1 ton of CO2. So how much damage does that do? This was one of the first individuals to actually calculate this number. So his name is Bill Nordhaus. Little story about Bill. When I was a graduate student, still had long hair and I was still smoking. We were all silly when we're young. I gave my first talk at a big conference. I had real pants for the first time in many years. And I gave a talk and there was a guy in the back who kept on giving me a really hard time with these amazing questions. And I was like, who is this guy? He must be really, really brilliant. Turns out it was Bill Nordhaus. The famous people never wear name tags because everybody knows them. So Bill started thinking about, how do you figure out that number very early? He was one of the very first ones to really think about how you actually physically calculate this number in a spreadsheet, and did so. He's made contributions in much broader areas of economics, but if you read his Nobel Prize, large parts of it are due to the work on the social cost of carbon. So this is real science, right? This is not some made-up number that somebody is trying to use to lobby the government or something like that. In fact, there's an official process where the government itself calculates this number and uses it in its decision-making. What? How do you do it, Max? Okay, I'm glad you asked. So this is basically, and I'm going to send you later for those of you who like writing code, there's an open source piece of software that you can use to calculate this number yourself. It's a really fun thing to do. But for those of you who aren't going to do this, basically what you need is top left, you're going to need projection as to what the world looks like over the next, let's say, 300 years. How rich is it going to be, mostly, and how many people are there going to be? Sometimes you regionalize this a little bit, right? A richer society is more able to adapt to climate change, right? More air conditioners and so on, versus a poorer society is less able to adapt to climate change. A more populated planet is going to suffer more because extreme events are going to affect more people. So you have to come up with scenarios of income and population. You then have to translate that into emissions, right? These different states of the world, how much CO2 are they going to emit, right, as a function of income and population? And then you're going to come up with a trajectory of emissions out to 2300. Then you're going to take these emissions, you're going to plug them into a climate model. Whoa, this is already getting super complicated, right? You're going to feed emissions into a climate model, and that tells you what the damages are from that emissions trajectory on migration, energy use, and agriculture. And then what you're going to do is you're going to take the output from that climate model, which has temperatures and sea level rise, and you're going to look at what damages that does to physical sectors, right? So you're going to translate higher temperatures into changed migration patterns and energy consumption. And then you're going to come up with one line that tells you what damages are going out to 2300 in US dollars. You also have to make decisions like, how much do we value the consumption of future generations, right? The same as ours now, or do we downweight the consumption of our great-grandchildren, for example? Things economists have to struggle with. how do you get the damage out of 1 ton out of this? So you run it once with a baseline scenario, and then you give it a 1 ton increase in CO2 and you run it again. You look at the difference between the two, discount it into present values, and that gives you one number. And that one number is going to tell you what damage CO2, 1 ton, is thought to do over its lifetime if emitted in 2020. Usually I do a little bingo thing, but I didn't know what the setup was. So there's this new software called Poll Everywhere where people can take QR codes and vote what the number is, and then you see a histogram, but it's right after lunch. I didn't want you to work so hard. The actual number the US government uses right now is $51 per ton. So drive your Ford from San Francisco to Chicago, you've done $51 of climate damage by burning the gas that you do during that distance. You might be thinking about, Max, that's impossible that that's a ton, but gasoline into CO2 picks up a lot of weight because you're picking up a whole bunch of other molecules during combustion, so that number is right. I've had it checked by real scientists. Okay, so let's slowly move over into policy. I'm about halfway through my talk here. For those of you keeping track, I've got this cool new counter that my spouse gave me because I tend to talk too much. So sometimes I get limited into how much time I get to talk about economics at the dinner table. But this is actually something that goes back to President Reagan, who required all federal agencies to calculate the benefits and costs of regulations they were going to impose, right? We can talk about the history of that, but if you don't like regulations, you always think oh, well, the benefits from this regulation are probably going to be less than the costs, so fewer regulations. Turns out if you do this right, a lot of regulations do not pass the benefit cost test. There's formal procedures as to how to calculate these numbers, and it gets really interesting for folks like me as to how you actually do this. But this all came to the center of attention in terms of greenhouse gas emissions when in 2006, a court of appeals denied the Department of Transportation's attempt to place a $0 value on the benefits from CO2 reductions from fuel economy regulations. So they said, we know there's some damage number that you should use, and it's not 0. So what number are you going to use? Right, so we could keep on talking here about what happened, but basically under President Obama, he said, okay, let's get all the agencies together and jointly develop one number for the damage CO2 does in federal rulemaking. There were some of the biggest nerds in economics. Cass Sunstein, who's amazing. Michael Greenstone was involved. A whole bunch of people calculated this number and came out with what's now the $52 number. And then President Trump was elected, basically did away with the interagency working group in 2017, reduced the social cost of carbon to essentially $1 instead of the 52. And those of us in the scientific community said during those 4 years, we're going to lose 4 years of research work that the federal government would have done in response to a report the National Academies issued. So we're going to do that outside the federal process, push science along, that when a more climate worried administration comes in, the research will have been done and peer reviewed. That's of course always key. So before we switch over to buildings very shortly, is this number used a lot? This number is used across the federal government where energy is consumed in regulation. So this affects vehicles, buildings, energy efficiency, agriculture. Think about the things that emit greenhouse gases. So it's appeared in 80 plus. I think we're almost at 100 benefit cost analyses now with $1 trillion in total benefit. So this is big, big numbers. This is just for those of you who want my slides, gives you a sort of a history of how the social cost of carbon bounced around, but it started somewhere near 0, then got up to, in current day dollars, $52, then went back down under Trump, and now we're back at $52. Super exciting. I also felt like I needed to show you something that looks really scientific, because so far it all looked like cartoons, right? So what the EPA did here is they sort of visualized the analysis underlying the social cost of carbon. It's not sort of one number that one calculates, but there's lots of uncertainty analysis done, meaning how quickly does the climate system respond to higher emissions of CO2, right? How certain are we about how mortality responds to higher temperatures? So really fully reflecting the uncertainty inherent in any sort of function, and runs these Monte Carlo analyses. So all of these are sort of distributions of the number, and the number we use is usually the average of one of these distributions. So, beautiful. Max, you promised me some new science. All right, here's the new science. One of the big things that economists worry about is, or environmental economists at least do, and I know folks in buildings too, is how do changes in the environment affect human well-being, right? That's pretty much the mission right there. So this could be direct impact on well-being. So if I'm inside and I can run an air conditioner when it's 110 degrees outside, I am better off. Somebody working on building envelopes or HVAC systems might really worry about what's the optimal building envelope for a certain, area or something like that. But we that look at the sort of more macro level in this business really just worry about a relationship, a dose-response function between, let's say, mortality and temperature. So how does mortality in Mumbai, for the average person living in Mumbai, respond to an increased extreme heat day versus mortality of somebody in San Francisco 100 years from now? So the reason we got really excited is this literature looking at damages from hotter days, more storms, and so on has absolutely exploded with, like most disciplines, the availability of amazing new data sources out there and computational methods and servers that just run much faster. So what you're seeing here in this particular graph is these previous models that were responsible for the $52. Most of what we know about how the environment affects human well-being comes from a time when counting crows was still at the top of the charts, right? Many of you might not even remember that time, a long time ago. But most of the science that's coming out here is from the last 5 to 6 years. So one of the jobs of folks like me and my colleagues here at Berkeley, we've got this amazing group of energy and environmental economists. Some of us loved, some of us not so much, depending on our opinions on certain topics. I got in a lot of trouble when I said something slightly critical of building codes once. Let's put it that way. All right. I'm generally in favor of building codes, but I questioned something and that led to a full inbox. Okay. So there are groups working on this. Most of it's privately funded. We have spent billions of dollars on studying climate change. 99.3% went to launching satellites and measuring glaciers and looking for ice cores and stuff like that. And less than 0.5% went on studying the social impacts of climate change. So we're slowly trying to change that, largely with private sector funding, but slowly also public sector funding. And the state of California has actually been really supportive of this work. So if you want to know more about what people are doing in this space, I would point you to Resources for the Future, a think tank in Washington, D.C., who's behind the work I'm about to show you, or the Climate Impact Lab, which is joint between Berkeley, University of Chicago, the Rhodium Group, and Rutgers. And then there's a bunch of one-off folks who were part of the National Academies process who are running around doing our own thing. That's me. Okay, so just to give you a flavor of how cool the science is now, let's just think about mortality, right? That's the worst outcome for a human, is if it's really hot outside and you cease to exist. So the question here is, how does extreme heat, for example, affect the risk of mortality? It depends on, your health status. It depends on your age. It certainly depends on your income and whether you're able to afford an air conditioner or not, right? I live in Lafayette, Walnut Creek. When it's 115 outside, I don't care. It's a cool, balmy, I'm going to lie to you, 79 degrees in my house. My wife always sets it to 71. I'm like, are you insane? That uses so much energy. But, internal household struggles. But what we need to figure out is different populations now across the world are going to respond differently. And as incomes rise, they're going to respond differently than they would now. So this is a big data effort out of the Climate Impact Lab that collected the most extensive data set on mortality across the world. there's some countries missing and they fill those in, so I would ignore the Africa numbers here. But the basic notion here is we're going to build in adaptation and see how an extreme heat day affects the risk of mortality, and then take that dose response function and dump it into the model, right? This was an update that took 4 years alone to compute. Now you're like, Max, where are buildings? I'm here for buildings, and you haven't had a single building in this thing. So let me show you what I think is one of the coolest graphs I have seen in environmental economics in many years. This is mortality on hot days in the United States between 1931 and 1959 on the left graph. So what you have on the x-axis here is temperature, or number of days, daily average temperature, sorry, you know, so 90-degree average temperature for a day, that's really hot. And what you're seeing is mortality goes up pretty steeply. So this is, you know, prior to the real explosion of incomes. And look at what happened if I look at the 50 years or 45 years after that. It's almost flat. So what is that? It's not that humans are all of a sudden cyborgs that have built-in cooling, right? It's the same humans, but we have air conditioning and we have buildings that shield us from heat outside. So what you do in designing buildings is you've essentially done that. So for your own holiday table, if anybody asks you, what do you do for a living? This is a really convincing graph that's going to get you an extra helping of dessert. All right. So that's amazing. And this is not modeled data. This is actually observed mortality data, actually observed temperatures, and using some data science tools that this afternoon's very cool session might, you know, employ as well, you know, and making graphs. The question you might ask is, does this make a difference? All this science, better mortality dose response functions, better energy response to temperature, and so on, does that change the number? And what this graph does is, yes, it does, right? So the old model essentially said that 30% of climate damages are going to come from energy consumption. That's absolute nonsense, right? There is no way that that makes any sort of sense. If you update the data to what we see now using actual electricity and natural gas consumption and liquid fuels consumption, that number is almost zero in terms of what happens, because winters get milder, summers get hotter. You get a lot of savings of energy in the winter, and you get you know, higher usage in the summer, but there's a trade-off there. It's more complex than that, but that's the basic notion. In the past, we've also drastically underestimated the damage that heat does on mortality. So if you build that in correctly, the mortality damages go up. And then we're working on labor productivity as well. So here's the paper you should read. I'm not an author on this paper, but the other German environmental economist whose favorite soccer team is also Bayern Munich, because all the other soccer teams are just not as exciting. The other ones win all the time. They have this lovely paper with just an army of all-stars. Some of these are just my heroes in my field right here. This reports out a fully soup to nuts redone process for the social cost of carbon that is peer-reviewed in the best general interest science journal there is, right? This is the one you get a publication in Nature. People around campus are going to sort of like wink at you and go, yeah, nice job, Max. But what they show here, to make a long story short, they do an amazing amount of science. All of it's open source, so you can replicate this. But their mean number went from $52 to $185. So a tripling of the social cost of carbon, and they're not hiding anything here, right? If you want to go even higher and you use discount rates that are a little bit lower, it's very easy to get to $300. Also, there's only 4 sectors in here. There's only agriculture, there's energy, mortality, and sea level rise, with agriculture and mortality being the 2 big affected sectors here. Is this now the official federal government number? No. Do I have inside information? Maybe not really. So those of us who've seen things are sworn to absolute secrecy, so I'm not going to reveal anything that I might know that I'm not supposed to say. But I think it's completely fair to say that federal policy has usually, since it's obligated to do so, used best available science. Papers published in 1990 and 1995, or this, I think they're going to start gravitating towards work like this. So I don't think it's unreasonable to assume that if the social cost of carbon were updated, it will no longer be $52 and it's not going to move towards zero. So for the rest of my time here, I'm just going to assume that, $185 is a number we're headed towards, or let it be 150 or anything like that. I don't know what that number is. Why should you care, right? So this is my desperate attempt to seem relevant to this audience right here. So whether this number is true or not. So I looked at DOE. DOE said commercial buildings generate 16% of all US CO2 emissions. So I started doing back of the envelope numbers, and there's a range here of how you could get at that number, but it's certainly not an insignificant share of CO2 emissions. We are also committed for now to a path to net zero, right? So whatever emissions come out of buildings is going to have to be zero or close to zero or negative, which is going to require just absolutely massive reductions from the sector. Now, while we in the US often worry about, how do I get this? I really love brutalist architecture. By the way, maybe I grew up in neighborhoods where buildings looked like this. So how do you take this thing that's going to be a hotel and make that remotely net zero-ish, right? That's a big question. The other issue, of course, being that just fixing the problem in the US is not going to help us much. This needs to be a global effort where in lots and lots of places, I don't know if I go to China every year, or I haven't been since the pandemic, but I usually go every year. And some cities are just unrecognizable year after year. So the amount of new construction that's taking place globally is still quite impressive. So here's one way to look at it. If the government puts a higher social cost of carbon in place, most people react with, oh my God, now what I do is more expensive or more difficult, and I'm going to have more arguments when I do my environmental impact statements and all of these things. I'm going to put a positive spin on it, all right? The value of energy efficiency, or the value of a ton of avoided greenhouse gases, has just tripled, right? So you're shifting the attention to what should we do in terms of the environmental footprint. You're just simply placing 3 times the weight on CO2 emissions that you did before, right? The thing to keep in mind, too, is that right now this is just science. This is not policy yet, but I will eat this shoe if there's not a significant update of that number coming. So what does this mean for new construction, right? I read all these tweets and blogs, and there's so much advocacy going on in this space, and it's really interesting, right? Right now we're obsessed with heat pumps, and we're obsessed with getting natural gas out of every single building in the world, and that's an interesting strategy right here. But I think thinking through really carefully, what are the greenhouse gas implications of technological choices we make here, both in terms of on-site and off-site generation, right? And how do we power these buildings is absolutely key. Because from an economics point of view, we always call these durable assets. What you're putting in place now is going to be around for 15, 30, 50, 100 years, okay? There's also the issue of where do we generate power to, make reliability a thing? Do we, like in the old days, put little gas-fired turbines or diesel generators outside of hospitals? Or are we going to really think about oversized battery storage systems near these facilities? The one number that we just don't have a good number on, and folks like Catherine Wolfram, who was Deputy Secretary of the Treasury until yesterday, I think she just finished her term, has been working on this really hard, trying to figure out how much do people value in dollar terms the fact that your lights are on, right? How annoyed do we get by power outages? The answer is very, but in dollar terms, that's a really tricky thing to figure out. So we're going to get some better numbers on that soon. The thing I find that I lose a lot of sleep over is not necessarily new construction, right? That strikes me in some sense as not an easy, but an easier problem. But if we're looking at our existing cities and we're trying to think about how to retrofit massive amounts of old construction into net zero buildings, this becomes, I think, quite the challenge across North America and worldwide, where we have I'm from Germany. There's still lots and lots of buildings which have basically diesel furnaces. I mean, heating oil furnaces in the basement, and then a big truck shows up. They pump this in your basement, and that's how you heat your home or your building. And how do you retrofit this with, gas? Even is a big question. But how do you take this all the way to fully renewably powered homes? So I know people in this room are working on this question, and to me, the value of coming up with answers to this through these papers here has again just tripled. Okay. The bigger issue here, and I talked about political economy earlier, is an old principal agent kind of issue. Well, it's not actually a principal agent problem, but something similar, where the benefits of you not emitting CO2 emissions accrue to humankind, but the costs accrue to the owner or the person building the building. So we've got to figure out how to do this. Firms left alone won't do it, right? Without government regulation or government push, people aren't going to take into account these numbers. So whether we do this through benefit cost analyses, environmental impact statements, or what I would argue is real carbon pricing, is really the avenue forward. Not the favorite thing that everybody likes to hear, but that's it. I know we've all learned about, scope 1, scope 2, scope 3 emissions. I actually think somebody in this room, explained to me the exact difference. So many of you know a lot about this, but the same building in two different places is going to have vastly different emissions depending on what grid powers your building. So a lot of policy I'm seeing right now is assuming that the grid is going to be clean in the next 20, 30 years, and we're just going to go ahead as if. But I'm still a little bit worried about the decisions we make in different places, assuming that all places are going to be equally clean in the next 20 to 30 years. So really thinking about, again, from soup to nuts, what's the environmental footprint of a building project is going to become more visible. All right. Question is, why should a profit maximizing firm change? So I'm thinking of large enterprises that invest in this sector. And I did 2 summer internships at McKinsey. So this is a McKinsey study. And I decided that I cannot wear a suit every single day. You have to dress more conservatively than your client. And I worked in mergers and acquisitions in German banking. There is nobody more conservatively dressed than a German M&A banker. So it's like a 4-piece suit you're wearing to work every day. I can't do it. But really clever folks, and they ran these studies here that are kind of neat. I think I got this out of I have to check. No, it's McKinsey analysis. That's right. So they just basically went through the literature and sort of looked at, what's the impact of firms at least proposing ESG activities, right? So sustainability is just one part of this. There's also governance and other factors that play in here. And the argue here is this is positive, has a positive impact on returns. So doing the right thing creates shareholder value is what the study says. The causal inference heart that beats inside me is always like, I don't know, right? So I want to see more work on this. Do we really get significant shareholder returns from these activities, which are clearly the right thing to do? Okay, I'm almost done. I have 1 more minute. We talk about climate. The thing that right now kills many, many more people than climate change is local air pollution, right? It is the #1 environmental killer out there in North America. If you go to China or India, you just need to fly in and see it. This is Seattle today. So outdoor air quality is really terrible. But this is purple air, and I know purple air has issues, some. But overall, the cool thing about purple air, which we didn't have before, is we had measurements outside people's homes and measurements inside people's homes, because some like me have 2 monitors in our homes. And what we're seeing is we're just seeing off the charts readings inside people's homes. So while we're working on doing something about greenhouse gas emissions, it would be reckless not to think really, really hard at the same time, what are the implications for people's exposure to pollutants as the outdoor environment deteriorates in terms of increased frequency of wildfires and so on, and how we can protect ourselves from being exposed other than wearing an N95 mask each day. All right, so I went 5 minutes over. If you have questions, this is my email address. I answer all my emails slowly, but I do. So feel free to reach out anytime. Also, if you want to get in touch with somebody, do you know somebody at Berkeley who works not on what you talked about, but on whatever? This place is unbelievably hard to figure out who does what. And those of us who've been here for a while are pretty good at dispatching folks. So definitely feel free to reach out, and I'm happy to take any questions. Thanks.